So in the last video, for the first time in this section, we did not come up with a new rule. I mean, I guess we kind of did come up with a new rule for rational functions by doing a lot of really complicated algebra and coming up with this thing that's crossed out. But what happened when we looked at this really carefully is we noticed that it's really just the power rule going on here. So rather than define a new rule, we kind of extended the domain of our old rule. We only proved the power rule with the whole Pascal's triangle argument when the exponent was a positive whole number. But what we learned is that power rule works even when that exponent is a negative whole number, which is kind of cool. We can deal with this special form of rational functions without any new rules. Okay, cool. But what about this special form of radical functions? What's the derivative of the square root of x? Well, first thing I'm going to say, you could probably predict, we already know how to do this. We could do it with the difference quotient. And you're like, let me stop you right there. I don't want to see you do this again. I know how to do it. There's a little trick. You multiply the top and the bottom by the conjugate of the top. Stuff cancels out really nicely. You change all the h's into zeros. You get your answer. I can do that. I don't need to see you do it again. Okay, good, because I don't want to do it again. Because really, I'm not interested in coming up with the derivative of the square root of x. What I want is the derivative of the nth root of x. I want a rule that will work for any root, not just the square root. So for example, the cubed root. Could we do an argument very similar to the argument that we've been doing for the square root if our function was the cubed root of x? Well, kind of. I mean, we'd set things up the exact same, and then the trick that we would have would be the exact same. We need to cancel out this h. The way we're going to cancel out this h is by finding the h up in the numerator. The way we're going to find the h up in the numerator is we're going to rationalize. We're going to get rid of the square root signs, or I guess cubed root signs in this case. How do you get rid of the cubed root signs? Well, there's a trick, kind of like our multiply by the conjugate trick. Unfortunately, it's not just multiplying by the conjugate. There is something you can multiply the top and the bottom by, but it's more complicated than just the conjugate. It sort of looks like the conjugate, but there's more terms. And the bad news is it's going to change for the cubed root or the fourth root or the fifth root. I'd have to teach you something different to multiply the top and the bottom by every time you're trying to use the difference quotient here, which is sort of a bummer. But I've got good news for you. If you went through and did all this simplification, maybe you can even see it, what I'd be left with up in the numerator would be x plus h minus x, because the f in FOIL would get rid of the square roots on the x plus h's, the o and the I in FOIL would cancel out, and the L in FOIL would get rid of the square root on the x's. And the great thing about x plus h minus x is the x's cancel out, so I'm left with just an h up top. And after those x's cancel out and I have just an h up top, I can cancel that h with this problematic h and get that this is the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And the great thing about this as a function of h is it's continuous at h. In other words, I can change all the h's into zeros to evaluate this limit, and I get 1 over the square root of x plus the square root of x. Wait, the square root of x plus the square root of x, isn't that just x? No. The square root of x times the square root of x is just x. The square root of x plus the square root of x is 1 over 2 times the square root of x. Okay, cool. You said you weren't going to redo this problem, and then you just redid this problem. How does that help me come up with a general rule for the derivative of any root of x? Well, look what happens if I change the form that I write this question in. What if I don't consider the square root of x written in radical form, but instead think about the square root of x written in exponent form? Maybe you recall from like a pre-calculus class or something that the square root of x is the same as x to the 1/2 power. So I could rewrite this question as, what's the derivative of x to the 1/2 power? We haven't proven that the power rule works in this case where the exponent is a fraction. We've only proved that it works at first when it was a positive whole number and then when it was a negative whole number. But let's give the power rule the benefit of the doubt and just assume that it works. If the power rule did work, maybe equals question mark, because I'm not sure if it works, what I would do is I'd bring that 1/2 out in front, and then I'd subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. If the power rule worked when the exponent was fractional, the power rule would say that the derivative of x to the 1/2 power is equal to 1/2 times x to the negative 1/2 power. But what is 1/2 times x to the negative 1/2 power? Well, first, when you have negative exponents, that means take the reciprocal of. So I could rewrite this as 1/2 times 1 over x to the positive 1/2 power. I can account for the negative by putting this down in the denominator. And then x to the 1/2 power means the square root of x, as we wrote up here. So this would be the same as 1/2 times 1 divided by the square root of x. And when I have two fractions multiplied together, I multiply straight across. What I'm trying to say is this answer that we came up with using the power rule is 1 divided by 2 times the square root of x. Does that look familiar? 1 divided by 2 times the square root of x? It should, because it's exactly what we got up here as the answer. That is not a proof that the power rule works when you have fractional exponents. That's just evidence to that case. It appears to work in this specific case. Does it always work? Well, as your math teacher, I can tell you that, yeah, it always works. This is a case where I'm going to kind of cheat and not really prove to you that it always works, because in order to prove to you that it always works, I have to show you how you can get rid of the cubed root of the fourth root of the fifth root, which involves algebra that's probably not going to benefit you all that much. And I think there's better uses of the time you're willing to grant me. So maybe I'll just ask you to trust me that when we wrote the power rule seemingly hours ago, and I didn't put a little asterisk here being like, be careful, make sure you only use this when n is a positive whole number, because we only proved it using Pascal's triangle when n is a positive whole number. I purposely didn't write that. The awesome thing about the power rule is I don't need the little asterisk on the n. This always works. We've proved it works for positive whole numbers. We've proved it works for negative whole numbers. And I've shown you an example where it works for a fraction. And I'm just asking you to trust me that it works for all other fractions. So if I really want to know the derivative of the cubed root of x, and I didn't want to figure it out with this really complicated way of getting rid of these cubed roots, what I could do is rewrite this problem in a form that's conducive to the rules that I have. Instead of considering the derivative of the cubed root of x, I'd consider the derivative of x to the 1/3 power. Written in this form, it's easy to apply the power rule. Playing the role of the n in the power rule is the 1/3. So you bring the 1/3 out in front, and then you have x raised up to whatever I get when I take that n and subtract 1. 1/3 minus 1 is negative 2/3. Why? Because 1/3 minus 1 is the same as 1/3 minus 1 over 1, which is the same as 1/3 minus 3 over 3, which is the same as 1 minus 3 over 3, which is the same as negative 2 divided by 3. The derivative of x to the 1/3 power is equal to 1/3 x to the negative 2/3 power. As far as I'm concerned, this is a perfectly fine answer to this question right here, but I can just tell you it's not the standard way people would write it. Because typically when the question is given in radical form instead of exponent form, the answer should be given in radical form as well. So what I really should do is say this is the same as 1 divided by 3 times x to the positive 2/3 power, because negative exponents mean take the reciprocal, and then recognize that when I'm raising something to the 2/3 power, that's the same as taking the third root of x squared. All three of these things are mathematically equivalent, although most teachers would tell you that this is the preferable answer to give. But really, I got to kind of pick my battles. And frankly, if you're able to take the derivative and get any of these answers, I'm pretty happy. The big takeaway here is much like in the previous video, where we did not come up with a new rule for rational functions, or at least this special form of rational functions. In this video, we're not coming up with a new rule for radical functions, or at least not these special forms of radical functions. All we're doing is extending the power of the power rule. The power rule is even more powerful, pardon the pun, than it was before. We can use it on cases like this, which ends up making problems like this fairly easy. Before I end this video, one more thing I want to show you. What if somebody asked you for the derivative of x to the 5th power times the square root of x? It would be really cool if the derivative of the product of these two things, x to the 5th times the square root of x, was just the derivative of the first thing, x to the 5th, times the derivative of the second thing, the square root of x. And you're like, yeah. I know you well enough at this point that when you talk like this and say, it would be really cool, it's going to end up working out, right? These things are going to end up being the same. Turns out, no. So this is where you have to be really careful. One of the big challenges with calculus is not just learning how to use the various rules, but learning what apparent rules are not actually rules. And it turns out that the derivative of a product is not the product of the derivatives. Don't believe me? Let me prove it to you real quick. I know the derivative of x to the 5th power. That's really easy. The derivative of x to the 5th power is just 5x to the 4th power using the power rule. And guess what? I know the derivative of the square root of x also. That's something I just learned how to do. I think about it as the derivative of x to the 1/2 power, and then I use the power rule again. It's 1/2 times x to the negative 1/2 power, and if I'm feeling especially ambitious, I rewrite this in a different form to get rid of the negative exponents and the fractional exponents. I'm not feeling ambitious, so I'm going to leave this as 1/2 times x to the negative 1/2 power. The stuff in blue is equal to what we have right here. And what we have right here can be simplified. This is 5 times x to the 4th times 1/2 times x to the negative 1/2. So I can think about it as 5 times 1/2, in other words 5/2, times x to the 4th times x to the negative 1/2. And maybe you remember that when you're multiplying together two things with the same base, you add their exponents. X squared times x to the 5th is x to the 7th power, for example. That same logic works here. X to the 4th times x to the negative 1/2 is x raised up to whatever 4 plus negative 1/2 is. 4 plus negative 1/2 is the same as 4 minus 1/2, which is 3.5. In other words, 7/2. What I'm saying is the stuff in blue is 5/2 x to the 7/2 power. Compare that with the stuff in green. And you're like, how do I compare that with the stuff in green? I don't know how to take the derivative of a product. You just told me it wasn't the product of the derivatives. So if it's not the product of the derivatives, what the heck is it? Well, we don't know what it is, but fortunately we can rewrite this so that it's not a product. What we have in green is the derivative of x to the 5th power times x to the 1/2 power, because the square root of x is the same as x to the 1/2 power. And much like over here, when we had two different exponents with the same base, we could add up the exponents. We can add up the exponents here. X to the 5th times x to the 1/2 is x to the 5.5 power. In other words, x to the 11/2 power. What's the derivative of x to the 11/2 power? That's easy. Just use your power rule. Playing the rule of the n is the 11/2. So it'd be 11/2 times x raised up to the n minus 1 power, 1 less than 11/2. 11/2 minus 1 is 9/2. Think 11/2 minus 2/2. So the stuff in green is equal to 11/2 x to the 9/2 power. Note that these two things are not the same. 11/2 x to the 9/2 is not the same as 5/2 x to the 7/2. Wait, what just happened there? The derivative of a product is not the same as the product of the derivative. Yeah, it would be really cool if it was. Is it? Nope. And here's an argument showing that it's not. If you didn't follow that argument, maybe you'll like this argument better. What's x times x? X squared? Right. So the derivative of x times x better be the exact same as the derivative of x squared. What's the derivative of x squared? Well, I can just use the power rule, right? And get 2x to the first power. In other words, 2x. Yeah. If the derivative of a product was just the product of the derivative, then to take this derivative, maybe I'll put a big does not equals here, I could just take the derivative of the first x and multiply that by the derivative of the second x. But I can't do that because the derivative of x is just 1. And 1 times 1 is just equal to 1, and 1 does not equal 2x. Those are not the same thing. Very important to know that the derivative of a product is not equal to the product of the derivatives. There is something called the derivative product rule, but it's significantly more complicated than what you see up here, and it's not something we're going to learn in this section of videos. So earlier when I said sometimes when you're taking derivatives, you really want to show a lot of steps to really show your work because it's so easy to do steps that aren't correct. What I had in mind were examples like this. The big takeaway from this example right here is that we have to be more careful than maybe we realize that we have to be, because not everything with derivatives works out in the way that you would like it to work out. So maybe I could start the next video by coming up with a summary of exactly what we've learned, and maybe you'll understand now why going forward I want to be so careful in showing all the different lines and the steps of what we're doing, because taking derivatives is a lot more subtle than maybe you would think.